So far, the models that we've looked at, now we've tried them both right now and they both failed us. It's okay. That doesn't mean they're the only ones out there. It just means that they're not going to work for this particular data set. It's okay. All is well. So the first model we looked at was linear. We like that sometimes when it works, when it makes sense. So we looked at a linear model. So what was the big takeaway for linear models? Let's use blue and green. Yeah, that'll be good. What do you remember about linear models? And I'm only going to draw one on the board. I know that linear models can have positive or negative slopes, or even zero slopes. But I'm just going to draw one with a positive slope, just because. Ish, something like that. It can be noisy, obviously, it can be noisy. But what's the big takeaway, friends? What's the big takeaway about a linear model? What makes it linear? When you have a set increment of x and a set increment of y, those set increments, no matter how small, the ratio of those x's and y's stays constant. So this change of x here and this change of y is going to be the same ratio as this change of x, we'll call it x sub 1, change of y sub 1, this little change of x sub 2, change of y sub 2. They're all the same. That's what makes it linear, is that those stay constant. So you end up with this constant rate of change. Good! You probably learned it as change in y over change in x at some point in your mathematical careers. y2 minus y1 over x2 minus x1, however makes you m, a, whatever you want to call it. Good! And that was great! Until it wasn't. Until you put me on a bike. Thank God it's not today. Been more interesting today, though. You're one less person going back into the classroom, i.e. me. So, it was a brutally cold commute this morning. It took me 10 minutes to get my fingers to warm back up. Whew. It's been a while. It's been a brutal winter so far. I love it. How's I going with that? Oh yeah, but the linear model didn't fit me. What do we need then? Quadratic. Then when we launched over to quadratic. Now you probably didn't know why the quadratic model made sense for that. But if you've taken a physics class before, you do, because gravity is quadratic with velocity. So it's a change in velocity per second. So meters per second, or feet per second. If you've never taken a physics class, don't worry about that. Just, yeah, exactly. But if you have, you'll know why quadratic models make sense. It just so happened that it looked perfect. And I want to come back to why I say looked perfect and why this doesn't look perfect. Then we move to a quadratic model. Now, the ones that have fit for us, the quadratic models that fit for us, i.e. the bike model, we started, blue. We started near 0 with my bike data, and then it began to curve upward. So it looks something like this. Okay. And technically speaking, it goes back forever. And at some point, that guy is going to start curving back upward, yes? Now that's what a parabola looks like. It's got a curve, it's got a belly. When you look at the quadratic model for cancer rates from a couple, if you did that quiz, I'm not sure if you did it or not, but the quiz from a couple back, where you had the cancer rates that was shaped like a parabola, those parabolas go on forever, but the spot of data we were looking at was limited. So we didn't bother looking at this going backward because I wasn't back there. I started here. So we took the part of the curve that we liked. And could we argue that me on my bike would keep picking up distance, assuming the hill kept the same tiltedness? So if I was out there at, I can try this sometime actually, I can figure out what terminal velocity is. Go out to like Drinkwater Pass on 20, which is at like a 5 mile, 6% grade, and just put myself at the top and have people with stopwatches every 50 feet. What are you guys doing in the summer? Too hot anyway. Helping me, there we go, helping me. I'll get you to run next to me. But the idea is that curve would essentially keep going to a point. Eventually I'd hit terminal velocity on a bike, because eventually you end up getting wind resistance that's going to overcome the force of acceleration. But nonetheless, arguably, if that hill was about 100 feet longer, wouldn't I just keep picking up this pattern? Good. So what are you looking for with quadratic? What are you looking for with quadratic behavior? So what differentiates quadratic data from linear data?
It curves.
The curviness of it, right? All of a sudden, if we try to draw slopes on there, they aren't constant anymore, right? If I do a change in x and a change in y, and the same change in x and the same change in y, what starts happening to the changes of y's after a while? The changes in y's get bigger compared to the changes in x. Do you remember which changes were constant in quadratics? You might remember this, you might not. It's okay if you don't. Say that again. Which rises? I love that, Amber. And we only mentioned it once, and it was a bit ago. I might make a quiz up for this one too. It might be kind of fun. But here's the deal. Here's the deal. When you have a linear, let's make up a linear model. Make up a linear model. X, y, boom. Let's make y equal, I don't know, 2x. Let's just make it simple. And start feeding in x values. -1, what the hell? -3, -2, -1, 0, 1, 2, 3. Boom. There we go. Happy. What are the y values that go with those x values? -3? -6? -2? Where's your constant slope? Where's your constant slope? It's right here. That's up 2, isn't it? Up 2, up 2, up 2, up 2, and so forth and so on, up 2. And I called those, it's been about a week and a half since I call those first differences. The first differences in the y values. So for an up of 1 in the x, it's an up of 2, change in y over change in x. Constant rate of change. Perfect. How does that change with quadratics? Yes, you remember, Katie.
The second difference.
Yes, you remember. Hell yeah, you do. So if you make a quadratic, let's make a nice quadratic, not the one we used with my bike because it was a little messy. But this works for any quadratic model. I apologize, Tom, you actually tried to do that one in the homework that was trying to prove it in general. You're like, the hell with this. It's okay. This is all you need to take away from it right now. How about y equals x squared? Let's make that model. And we'll use the exact same x values we did over here. -3, -2, -1, 0, 1, 2, and 3. Cool so far? Cool so far. Now what are the y values that go with that? Okay, just what a parabola should do. Symmetric. Now take a look at the first changes in y, like we did right here, the first differences in y, shall we?
It's 5, 3.
Right, that went down 5, didn't it? When 9 to 4, that went down 5. That went
Down 3.
That went
Down 1.
up 1,
3.
up 3, up 5. Now that is hardly constant. Some are negative, some are positive, yes? But what happens when you bump out to the second differences?
It's 2, 2, 2, 2.
Huh. Up 2, up 2, up 2, up 2, up 2. Hell yeah, and that's what makes it interesting. That's the characteristic quadratics have. Cubics have it too. Cubics have a difference, but you have to bump out one more. So Usain Bolt's model that you guys used, you used the cubic model, I think, at the end, right? You would see a constant difference if you went one more. You wouldn't see a constant difference here or here, but if you bumped one more, you'd see a constant difference. And if it was a quartic model, you have to go out one more. So every other polynomial term you add, you have to bump out one more, one more, one more, one more. Fair enough? Fair enough. Good. That's where we are right now. So the problem that we're seeing right now is, does the data we have look quadratic? So I don't know. Let's use Excel to help us out here, okay, a little bit. Okay, let's use Excel to pull us. No, I need the board, don't I? Yeah, I do need the board. See if I can make it. This is not bad actually, or it is. Here. So here's our data from our results in class. What I'm going to do is I'm going to create a column here and here, first differences, second differences, and see if there's any kind of a consistency there. Okay? Let's see. This is the best part about statistics. So, Katie, if I may, first differences. So what I'm going to do is I'm going to do, let's see, I was doing from here to here is that I have to do equals this one minus that one. Does that make sense? Did it drop 13.1 on average? Looks like it did, yeah? And if I drag that bad boy down, okay, there are my first differences. Hardly constant, But we knew they weren't going to be, because we ruled out the linear model already, right? We said the linear model's bunk. Doesn't make any sense. Let's try the second set of differences. Okay. Second. Spell that right? Second differences. So now we're going to do equals that one minus that one. See what these look like. What do you think? Yeah, it's oh, you can't see it. Can't tell mathematically, no, you just can't see it. You know? I don't know. I mean, that one jumps out of something weird's going on with that one. These are getting kind of close. Well, close-ish. It's definitely not as nice as that. 2, 2, 2, 2, 2. But even if it's not exact, the problem is that guy. Should we keep going with third differences?
Sure.
Should we even bother? I'm not sure we should. And why am I saying that? The problem is that. This is so different. The first one to the second is so different. We could totally do it. I mean, I'm not saying don't ever do something like that. But I'm saying I don't think we're going to see anything useful from it if we go out to a third set of differences. Equals u minus u.
It's gonna be the same.
It's going to be, yeah. See, these guys, so the problem is that first to second data point. Now, eventually, if we go out far enough, these are getting smaller, yes? So eventually, they're going to get close enough to this data point. The problem is with only 9 of them, we're going to run out of trials before we get there. And that's bad statistics anyway, trying to force a model on data that you aren't sure what the model is. Jeremiah, what are you thinking about?
I was just wondering if that first data point, is that actually a data point, or is that just trial number 0 with 22?
It is, but we have to count that because 22 of you started the experiment. And we kept track of the iterations, who was left in each one. Thank you for that. As Tom's question echoed. We have to use that. Jeremiah is questioning, as you should sometimes, question the first data point. And make sure, actually question any data point that looks unusual. Jeremiah, if I may, I want to return back to our TI screen. Because, let me ask this question. Does it look like that first data point is somehow odd when you compare it to the rest of them?